Welcome to lecture 15, where we start calculating limits of sequences. And let's start with this example. Let's evaluate the limit of the sequence n squared plus 3n plus 5 divided by 4n squared minus 7n plus 8. Let's take the limit of this sequence as n goes to infinity. Well, we can immediately say that the limit of this sequence is equal to 1 divided by 4. What is the idea behind this? Well, the idea is the following, that basically the highest powers are the strongest, so that basically this sequence an, as n goes to infinity, can be approximated with taking just the highest power at the numerator, n squared, and the highest power at the denominator, 4n squared, so that this is basically 1/4. So this is the way to calculate immediately at first sight the limit. If we want to give a formal proof of this, we can proceed in this way, and by just factoring out the leading terms. So this is the general rule. So that implies that we will have at the numerator n squared factoring out, so we'll be left with 1 plus 3 divided by n plus 5 divided by n squared. And at the denominator we do the same. We factor out n squared and we're left with 4 minus 7 divided by n plus 8 divided by n squared. And clearly we see that these elements will go to 0 as n goes to infinity. These will go to 0 as n goes to infinity. This will go to 0. This will go to 0. Therefore, we have that this will basically tend, because of course we will simplify n squared on top and n squared at the bottom, so we have finally 1 divided by 4. This method can be generalized, so we can say that in general, for a fraction of polynomials like p of n divided by q of n, what we can say is that if the degree of p of n is less than the degree of q of n, then we have that the limit is going to be equal to 0. If the degree of p of n is larger than the degree of q of n, then we'll have that the limit is going to be plus or minus infinity, and of course depending on the sign of the coefficients of the leading terms And if degree of P of n is equal to the degree of Q of n, then the limit is just given by the ratio of the coefficients of the leading terms. Now, this rule uh, uh, can also be applied, so the same holds for non-integer powers. Let me explain what I want to say with an example. Okay, let me give this example 2. Okay, example 2. Let's consider n plus 3n square root of n plus 4 divided by 2n minus 4n cube root of n plus 7. Okay, so we want to find the limit of this sequence as n goes to infinity. Well, it turns out that this limit will be minus infinity. Okay, okay, the idea behind this is always the same, just taking the leading terms of the fraction. So let me write down this. Let's suppose that this is an. So what we have, the idea is that an can be approximated as n goes to infinity to what are the leading terms? Well, on top we have 3n to 3 half, because in fact we have n to the 1 here and n to the 1 half. So 3n to the 3 half on top, and at the denominator we have minus 4. We have n to the 1, n to 1/3. If we sum 1 and 1/3, we have 4/3. So this is just equal to minus 3/4. These are the coefficients, and then we have n raised to the 3 half minus 4/3, which turns out to be n to the 1/6. And because n to the 1/6 it's just a power of n, will go to infinity, this thing will go to plus infinity, that multiplies then by minus 3/4. Of course this will go to minus infinity. So this is basically the proof of the limit. Again, but this is just the brutal proof of the limit. If we want to provide instead a formal proof, then as always we will need to factor out the leading powers. So what we have now is this. On top we will be factoring out n to the 3 half. So we have 1 divided by square root of n plus 3 plus 4 divided by n square root of n, and at the denominator instead we can factor out n to the 4/3, so that we have 2 divided by the cube root of n minus 4 plus 7 divided by n cube root of n. Okay, and as always, as n goes to infinity, this will go to 0. This, of course, will go to 0. This will tend to 0. This will tend to 0. So we have that this will tend to n to the 1/6, which is basically the ratio between n to the 3/2 divided by n to the 4/3 times minus 3/4. And clearly this is because this will tend to plus infinity. Plus infinity times a negative number, this of course will provide minus infinity. Let's consider another example. Let's go to example 3. In this case we have the sequence n squared minus n sine of n. Well, if n tends to infinity, we can certainly say that this will go to plus infinity. Now, how can we prove this? Well, the idea is that n to the square will become larger and larger. It will go to infinity much more than n sine of n will go to infinity. So if we want to prove this, we can say that n squared minus n sine of n can be reformulated as n times n minus sine of n. And of course this is larger than or equal of n times n minus 1, as we know that sine of n will be always between minus 1 and 1. So the worst thing can happen is that sine of n is going to be 1. But this term on the right hand side, of course this will go to plus infinity. This will go to plus infinity, so clearly this term on the right hand side will go to plus infinity, which will push by the squeeze theorem this term to plus infinity as well. Right, so let's now consider a new sequence, sine of n divided by n. Well, the same way we can say that the sine of n will grow slower than n. So this, as n goes to infinity, will tend to 0. If we want to give a formal proof of this, we can say that sine of n is always in between minus 1 and 1, and if we divide by n, which is always larger than 0, so of course the same inequality will hold. We have minus 1 over n less than or equal sine of n divided by n less than or equal 1 over n. And now, because this will go to 0, this will go to 0, by the squeeze theorem, once again, we have the sine of n divided by n tends to 0. Now, it is interesting that we can use these results for solving the exercise 3. Remember, the exercise 3 was basically evaluating this, right? So we can now write this not factoring out n, but factoring out n to the square. This will now multiply 1 minus sine of n divided by n. But we know now that basically this term will go to 0, so this will become basically n squared, that clearly will go to plus infinity. Okay, because we have n squared, we can say that this is n squared times 1, and of course this will tend to 1, this will tend to plus infinity, so clearly this will go to plus infinity. Let's consider now a little bit more involved example 5. Let's consider the sequence sine of logarithm. Remember that with this symbol ln is just the logarithm base e. So let's consider the logarithm of n to the square plus 7, and clearly this is possible. This is defined as this term is larger than 0 always, and remember that the logarithm is defined only for arguments strictly larger than 0. Right, so let's consider this sequence plus the cosine of n factorial. All this divided by square root of n. So we would like to find the limit of this fraction as n goes to infinity. Now we can immediately say that this will tend to 0. Why is that? Well, consider that on the numerator we have sine of something plus cosine of n factorial, but whatever happens, this cannot be less than minus 2 and cannot be larger than 2. So once again we can divide now by square root of n. So we have that sine plus cosine of n factorial divided by the square root of n will be less than or equal to divided by the square root of n, and larger than minus 2 divided by the square root of n. But now as n goes to infinity, clearly this will go to 0, this will go to 0, which by the squeeze theorem means that this will tend to 0, and so we have just proved the first statement. Let's go to another example, example 6. Let's consider now the sequence nth root of arc tangent of n plus 3. Well, this will go to 1. Okay, how can we prove this? Let's give a formal proof of this. Well, we know that the arc tangent of n for a positive angle n, this will be always between 0 and pi over 2. So we can extract, if we sum 3 to each and every term, we have that 3 will be less than or equal arc tangent of n plus 3, and this will be less than or equal pi over 2 plus 3. Okay? But now All these terms of the inequality are larger, strictly larger than 0, right? So we can take the nth root of each and every term. Remember that the nth root of x is strictly increasing. Therefore, because it will be a function with this behavior, so it is injective, therefore the same inequality holds, and we can write that the nth root of 3 will be less than or equal of the nth root of the arc tangent of n plus 3 less than or equal the nth root of pi over 2 plus 3. And now we know that this will go to 1, right? We just proved that, remember that we proved that the nth root of a for will go to 1 for every a larger than 0, and pi over 2 plus 3 is certainly larger than 0, so that is defined. The same way this will go to 1, and by the squeeze theorem the term in the middle as well will go to 1. Okay, another example, example 7. Let's consider now 3 to the n divided by n to 1000. Okay, we're considering a sequence which is just the ratio of an exponential with base 3 divided by a power. Now it turns out that this is going to be plus infinity. Okay, and let's prove this by using the ratio criterion. So an plus 1 divided by an, in this case, will be 3 to the n plus 1 divided by n plus 1 raised to 1000, and then multiplied by the inverse of n to of an, which will be simply n to 1000 divided by 3 to the n, but this is equal to 3. We have 3 by just simplifying 3 to the n plus 1 divided by 3 to the n, and then we are left with n to 1000 divided by n plus 1 to 1000. This is equal to 3. We can write this as n divided by n plus 1 all raised to 1000. And clearly we see that this will tend to 1 because the leading terms on the numerator is n, on the denominator is n, so the ratio is going to be 1 raised to 1000 is still 1, so clearly this will tend to 3. But the ratio criterion says that if an plus 1 divided by an tends to a limit L which is larger than 1, this will imply that an will tend to plus infinity, which is exactly what we wanted to prove. Right. So this result can be generalized, and this is an important generalization. We can say that the limit as n that goes to infinity of a to the n, an exponential, divided by n to the b, a power, is going to be plus infinity for every a larger than 1. We are considering now an exponential with the base larger than 1, which is clearly an increasing sequence, and for every b larger than 0. Okay, So we can say this is an important result, and we can write that the exponential wins over the power, right? So this is what we are saying. If we take the ratio of an exponential divided the power, because the exponential will grow faster to plus infinity, the ratio is going to be plus infinity. Let's now consider instead the example 8. And we will consider now the fraction n factorial divided by 312 to the n. And this, we'll see that this will go to plus infinity. So what we are saying is that the factorial wins over the exponential. Let's prove this again by using the ratio criterion. What we have then, we have that a n plus 1 divided by a n is equal to n plus 1 factorial divided by 312 to the n plus 1. This is a n plus 1. And now we need to divide by a n, which is just like multiplying by 312 to the n divided by n factorial. Okay? But now this is equal to n plus 1 divided by 312 by just simplifying the terms. And of course this will go to plus infinity as n goes to infinity. So and because the ratio goes to plus infinity, this will push a n by the ratio criterion as well to diverge to plus infinity. Okay, so we have another important result here. This can be generalized easily. So we can say that the limit as n goes to infinity of the factorial divided by any a to the n is always plus infinity for every a larger than 1. Okay, so another important result is that the factorial wins over the exponential. Okay, let's continue our review and let's consider now the example 9. Let's consider the sequence n n to the n divided by n factorial, and we'll see that these will diverge to plus infinity, meaning that n to the n is more powerful than the factorial. And let's prove this by once again applying the ratio criterion. So we need to first evaluate the limit of n plus 1 divided by a n, which in this case is n plus 1 to the n plus 1 divided by n plus 1 factorial, and then times n factorial divided by n to the n. Now we can rewrite this fraction as n plus 1 times n plus 1 to the n, this is the first term raised to the n plus 1, times n factorial, divided by n plus 1 times n factorial, all this times n to the n. And we can simplify n plus 1 and n plus 1, n factorial and n factorial, so that we are left with clearly this was n plus 1 to the n. Okay, so we are left with n plus 1 divided by n all raised to the n, which is clearly something that will tend, we can rewrite this as 1 plus 1 over n all raised to the n, but we know this limit. This will tend to e, the Euler's number, which is 2.7, so is larger than 1. So we can conclude saying that because an plus 1 divided by an tends to e, which is larger than 1, then an, which is n to the n divided by n factorial, will diverge to plus infinity. So we have another important result. We can say now that the limit as n goes to infinity of n to the n divided by n factorial is equal to plus infinity now. So this is an important result. We can say that n to the n wins over the factorial. So up to this point we see that n to the n is the most powerful sequence as far as divergence to plus infinity is concerned. Let's consider now another example. Example 10. And the sequence that we would like to consider now is the nth root of n. And we would like to see what is the limit as n goes to infinity. Now, the first approach we could think of, let's see if we can see what the limit is by just rewriting this in form of a power. We can write this as n raised to the 1 over n. But when n goes to infinity, this gives rise to infinity to the 0, which is one of the undeterminate form. So no, we cannot see what the limit is by just using this reformulation. One possibility would be to use the ratio root criterion for estimating this limit. In other words, we can say that we would like to estimate the nth root of an, okay, with an being simply n. So the ratio root criterion says that if we estimate the limit of an plus 1 divided by an, well, that limit is going to be exactly the limit of the nth root of an. Now, an plus 1 divided by an is, because an is just n, this will be n plus 1 divided by n, but of course this will tend to 1. And you see why we could not use the simple ratio criterion in this case, because we have one of those situations where we cannot draw any conclusion. But instead, by using this ratio root criterion, we can finally conclude that the nth root of an, which in this case is just the nth root of n, well, this as well will tend to 1. Okay, let's see another example. of another interesting sequence. We have now the nth root of n raised to 20 plus 19 n to the 12 plus 15. Okay, so we have this sequence. And also in this case we can say that these will tend to 1. Now, a brutal way of seeing this is that just by approximating the term under the nth root with its leading term. So we can, in other words, we can say that basically this sequence is equivalent. It's just like saying that it is the nth root. What is the leading terms is n to the 20, right? But this is just like writing nth root of n, all this raised to 20. But we know that clearly this we have just proved that the nth root of n will tend to 1, so this will be just like saying 1 to the 20, that of course will tend to 1. Okay, so this is a brutal way of saying this. Now, if we want to be formal, instead, formal proof of this limit is the following. We can say that the nth root of that polynomial can be rewritten as follows by just factoring out the leading terms. But the leading terms now is of course the nth root of n to the 20. So what we have now is the nth root of 1, of course, plus 19, and well, we have just a fraction, 19 divided by n to the 8 plus 15 divided by n to the 20. And once again, as n goes to infinity, we have that this term will go to 0, this term will go to 0, so these will tend, basically these entire terms, let me use the other color, let me use the green color, so this entire term will tend to 1, so that implies that this will tend to the nth root of n to the 20, right, times 1. And we know at this point, by the what we said here, we know that this will tend basically to 1. Okay, so this proves the statement. We can make a general consideration now. We can say that in general, if an will tend to a positive real number, so something that belongs to the interval 0 plus infinity, okay, a positive real number, well, then we can conclude that the nth root of this sequence, a sequence that tends to a positive real number, these will tend to 1. How can we prove this? So what we are saying is that somewhere we have the limit L, okay, which is a positive limit, so it will stay on the right of 0. And of course, if we stay on the right of 0, we can imagine that L divided by 2 is going to be here, and 2L will be here. Now, saying that an will tend to L means that at some point an will be between L divided by 2 and 2L. So, of course, this is true definitively. So, we can say that after a while we know that an will be in this interval. So this is going to be an between L divided by 2 and 2L. Now, if we have this, we can take the limit as n goes to infinity of this inequality, and well, or better, first let's take the nth root of all the elements, all the terms of this inequality, and we can do that because all the elements are positive. So we can take the nth root of L divided by 2, which will be less than or equal the nth root of an, less than or equal the nth root of 2L. But now we know that this will be 1 as n goes to infinity. This will be 1, and by the squeeze theorem, once again, this will tend to 1. So this proves what we just said. So this proves that, again, if we have a sequence an that is converging to a positive real number L, then taking the nth root of an again is another sequence that will tend to 1. Now, well, this is another result, but going back to the previous case, the case that we have in example 11, okay, where we determine the limits of the nth root of a polynomial, it is easy to prove in general, we can say that every time we have the nth root of a polynomial, we can always say that this will tend to 1. Now, how can, well, this is another important result which is worth remembering. Okay, so the nth root of a polynomial tends to 1. How can we prove this? Well, again, by just following the same method. So we will isolate the leading term in the polynomial. We will factor out from the root, and exactly in the same way we can prove that the entire limit will tend to 1. Okay, as we have just another 2 examples of sequences which is worth mentioning. Let's consider, for example, the example, this will be example, I think this is going to be example 12. Yes, example 12. Example 12 is, let's take the nth root, this time of n factorial, divided by n. And we want to see what will be the limit of this. Now, if we try to apply a brutal approach to this, well, we immediately realize that this is going to be a fraction that has infinity on the top and infinity at the denominator. So this is one of the undetermined form. We will find out, however, that this limit is 1 over e. As a first step to determine this limit, let's first find the reciprocal. Okay, the reciprocal. The reciprocal is basically n divided by the nth root of n factorial, which is something that we can also rewrite as the nth root of, we have n factorial at the denominator, and of course we'll have n to the n at the numerator. And we can say that this we can represent basically with an this, okay? an is gonna be this. This is gonna be an, okay? So now we can apply the ratio root criterion. In fact, we are looking now at the limit of the nth root of an, and we know that we can get this limit if we find the limit of an plus 1 divided by an, which in this case is nothing else that n plus 1. Remember that an now is equal to n to the n divided by n factorial. However, we have already encountered this limit, didn't we? We have encountered this limit, and we saw that n to the n divided by n factorial is something that can basically will get the limit e. Okay, so we know that this an plus 1 will tend to e as a limit. We have already evaluated this. Therefore, it is easy now to see that n divided by the nth root of n factorial is going to be just 1 over e, which is just the inverse of the limit that we have just determined. Okay, so this is the proof of this other result. And as a last result, as a last example, let's consider the sequence n factorial divided by 2 to the n squared as n goes to infinity. Okay? And we'll see that this result is 0. So this is a little bit surprising, but this shows that an exponential with an exponent, which is n squared, is more powerful than the factorial. Okay, so let's try to apply once again the ratio criteria. And see what happens. So once again, we need to find an plus 1 divided by an. And this is n plus 1 factorial divided by 2 to the n plus 1 to the square. And of course, then we need to multiply by 2 to the n squared and n factorial here. Now, this can be rewritten as follows. We can write n plus 1 times n factorial, and then we have 2 to the n squared on top. And instead, at the denominator, we can write this as 2 to the n squared plus 2n plus 1 times n factorial. First of all, we can immediately get rid of the n factorial. But we see that we can also simplify the terms 2 to the n squared. And we are left with n plus 1 on top. And then we have 2 to the 2n plus 1. Which we can rewrite as, so we have n plus 1, and then we have 2 times 2 to the 2n, so if you like 4 to the n. But we know that this part, this is of course something that will tend to 0, because we know that the exponential is more powerful of any power, and therefore we can conclude that this limit is equal to this an plus 1 divided by an tends to 0. And now, because an plus 1 divided by an tends to 0, which is less than 1,